going to be approximately? Relative to 1. Is it going to be bigger than 1 or smaller than 1? Bigger. 1.1 times 1.1 is going to be slightly bigger than 1. And what's going to happen when you have 1 and you subtract something bigger than it? What? A negative number. And what happens when you try to take the square root of a negative number? Does not exist. So the limit as you come from the right isn't going to exist for that reason, namely because this graph doesn't exist to the right of 1. And so the derivative of our original function, so the slope of our function coming from the right of 1, isn't going to exist, probably because the graph doesn't exist to the right of 1. Look at the original function. Can we all agree that the graph doesn't even exist to the right of 1? So there's no way to follow the pattern of the slope coming from the right if you can't come from the right. Do you follow that? So there is no derivative as you're approaching 1 from the right. Now we're going to do the same thing, but we're going to look for the derivative as you approach 1 from the left. So everything is going to look identical. And so I'm really going to jump right down to here. With the exception of, it's going to say the limit as you approach 1 from the left of this simplified, rationalized expression. So let's think about this. If I were to plug in something slightly to the left of 1, 0.9. Let's go with that, hypothetically, 0.9. 1 plus 0.9 is 1.9. Agreed? With a negative out in front. Negative 1.9 over. What is going to happen to 0.9 when you square it? Positive. But how big is it compared to 1? Is 0.9 times 0.9 going to be greater than 1 or less than 1? Slightly less, right? And actually, the closer we get to 1, like if we were squaring something like 0.99999, it would be even closer to 1, but always slightly under. So you're going to get 1 minus 0.9999999 or something crazy like that. And that's going to give you a teeny tiny positive number. And the square root of a teeny tiny positive number is also going to be teeny tiny positive. Yes? And so negative 1.9 divided by a tiny positive number is approaching what? Negative infinity. So from start to finish, rewrapping our head around what we were doing, on our original graph, as we approach 1 from the left, the slope is approaching negative infinity. And when I show you what this graph looks like, both sides of what we just calculated will make complete sense. Does anybody know, before I do it, what that's going to look like? Nobody? What could you do? Let's say you were completely at a loss on a test, and you had no idea if these answers even made sense, because you don't have me talking you through it. And you wanted to see, well, what does this graph look like? Let me try to wrap my head around that. What could you do to see what the graph looks like? Yeah, but you can't, because it's a part of a binomial, you can't really do that. Go back to graphing 101 when you were in 5th or 6th grade and you learned how to graph. Just pick values. Pick some x values, plug them in, and see to the best of your ability and approximate where some points would be, and then connect your points, right? On this particular one, you can't plug in anything greater than 1 or less than negative 1. So the domain is only between negative 1 and 1. So maybe you'd plug in negative 1, get a y coordinate, plug in positive 1, get a y coordinate, plug in a couple things in between that you think might make your life easier, right? Something that you'd be able to take the square root of. I'm not sure. You could play around with it and you could ballpark it. But here I will show you what this looks like. Realizing that the domain is between negative 1 and 1 alone is a victory. So here's what it is. It's really just a half circle, right? Because if you wrote this as y equals, I mean, in hindsight, now that we know that, if we squared both sides, we would turn it into y squared equals 1 minus x squared. And if you added x squared over, it would be x squared plus y squared equals 1, which is a circle centered at 0, 0 with a radius of 1. We only have the top half of the circle, though, because technically, if it really truly did start out as a full circle, and you move things over and you square rooted both sides, you would need a plus and a minus. We only have the positive square root, so we only have the positive side of the circle. But, so here it is. So now if we focus in on, let me just do this to make it much bigger. I just went from -2 to 2. If we are approaching 1 from the left and trying to figure out what is happening to the slope as I approach 1 from the left, can you see how the slope is becoming more and more like -infinity? Yes? It doesn't exist right at 1 for 2 reasons. The slope doesn't exist there because it's an endpoint, right? But even if it was a circle and it started wrapping back around, the slope wouldn't exist there because it's a vertical tangent. Does that make sense? Kind of like whatever one I just showed you. That's a vertical tangent right there. It's like a little tiny moment in time where it's vertically aligned. So that makes sense of approaching 1 and looking for your derivative coming from the left, why it is -infinity. Because it's getting more and more negative until it's a vertical line. Yes? And then it makes sense why coming from the right it doesn't exist, because you can't approach 1 from the right on this graph. And therefore the slope coming in from the right doesn't make sense for a different reason. But algebraically, it's still kind of the algebraic work paired with what we now know the picture looks like should complete that concept for you. Any questions on that? No? Okay. Then a piecewise. Is this differentiable at 1? What was our takeaway yesterday regarding piecewise functions? Before we check for differentiability, check for continuity first. So first things first, this one ends at 0.1 what? This first interval, this first section of the graph will end at 1 comma. When you plug in 1, what are you going to get? 1. And this next section is going to start with an open circle, but who cares, at 1 comma, what happens when you plug in 1? 1, 1. So the end point and the beginning point are the same. Is it continuous? Okay, so we'll give it a check for continuity. So now it's actually worth our time to come in and look at what is the slope of this function as we approach 1 from the left, and what is the slope of this function as we approach 1 from the right. So f prime of 1 coming from the left. I'll use the alternate form of the derivative, which is the limit as x approaches 1. Which piece are we using if we're approaching 1 from the left? First or second? First. So I have to do f of x, which is the first function, x, minus f of 1, which is 1, all over x minus c, which in this case is x minus 1. So direct evaluation is obviously going to give me 0 over 0, but this reduces and ends up being just your limit as x approaches 1 of 1. So what is the limit of the function 1 as x approaches 1? What happens if I plug a 1 in for the x's that are here? What will I get? 1. Okay? So wherever this graph leaves off, at that moment in time, it had a slope of positive 1. In hindsight, why was that a dumb thing to even calculate? the long way? Why should I have known that the slope was going to be 1 at 1? Because it's linear, right? And this has a slope of 1. This one, it's not so dumb to actually do it out. And not that it's dumb, it's just sometimes we just get in the grind and we're trying to show. I would have shown it anyway, but now that we see that it's 1, makes complete sense. Now we're going to find the slope at 1 coming from the right. So again, alternate form, limit as x approaches 1. But since we're coming from the right, we're going to use the second f of x. So f of x is x squared, minus f of 1 is still minus 1, all over x minus c, which is x minus 1. Direct evaluation, 0 over 0, but pretty easily I think you can see x plus 1, x minus 1 factoring will take care of this x minus 1. And so to get our answer, we just need to find the limit as x approaches 1 on x plus 1. And what will that be? 2. So the slope when we leave off is 1, but then when we pick back up on our second piece is all of a sudden 2. Is it differentiable at that location? If something leaves off with a slope of 1 and the other one picks up with a slope of 2, is it differentiable? Is that smooth and continuous? No, that's a sharp corner point. So it was continuous because of the point check. It's not differentiable because of the derivative check. They don't match. They would have to match. You would need a line that ends with a slope of 1 to begin at a point on a parabola that kind of also picked up with a slope of 1 and then slowly transitioned out of it. That would make for differentiability. If the slope coming in from the left was 1 and the slope coming in from the right was 1, so you had that smooth and continuous transition. But if this one leaves off at 1 and then your parabola picks up at 2, that's a sharp corner point. Do you follow? Okay. I don't know how this would transition to a graph, but it's hard to see because I can't do a piecewise on my calculator, but I can draw over that as my first piece and this as my second piece. It's not overly obvious, but that's why we have the algebra to back it up. This one ends off as a slope of 1 and it's starting at a slope of 2. So all of those slopes that continue in growth between 1 and 2, you just skip it over. You slope to 1 and immediately jump to 2. And then it starts as a slope of 2 and it continues to grow. So you hit every slope as you get steeper and steeper. But you just jumped over that 1 to 2, so you create a sharp corner thing. Okay. One more? 2 more. 1 more. Why don't you try this one on your own to get started? Check for continuity first. Please be continuous. Raise your hand if you're done. Raise your hand if you're stuck. But that will be it. This one, to the right, is going to be more of a rational. Right? That's f of x. Minus f of 2. Right? All over x minus 2. If you can open it by rationalizing that. Does that make sense? All right. Anybody else stuck? What? Rare, but they write them so it's a word. Okay, so what is the slope coming from the left? And the slope coming from the right? Also 1/2. So there is a lot of notation. It does get confusing. It would not be a bad idea to just write the definition of the alternate form of the derivative on the side so that it's always right in front of your face. So first the check for continuity. This one ends at 2, 2, and this one starts at 2, 2. So the continuity is definitely there. So then when we do the f prime of 2 coming from the left, we're just doing the alternate form of the derivative using the first function. We're finding what is the slope of this function at 2. I only put the left because for the overall piecewise function, it is from the left. But for all purposes, when we're considering just from the left, all that means is do your alternate form of your derivative and figure out what is the slope of this guy at 2. So that would be f of x, which is, well, first of all, it's the limit as x approaches 2. And we can say from the left, you don't really have to have it there because we're really just trying to focus in on this limit, or this slope at 2. So our f of x is 1/2 x plus 1 minus our f of 2 is 2 over x minus our c value of 2. And then direct evaluation for that limit would give us 0 over 0, so we should clear fractions. That's the only way to manipulate something like this. There's no radical. There's, yeah. Oh, that was your water bottle. I saw something in the corner of my eye go up, and I thought it was your hand. He was just taking a sip of his water bottle. False alarm. Sometimes that peripheral vision gets you. All right, so I'm going to multiply by 2 over 2 to clear my fraction. Wait a minute. Before I do that, I'm just going to simplify the top to 1/2 x minus 1 all over x minus 2. Good? So then, clearing fractions, if I distribute up top, that's going to leave me with x minus 2. On the bottom, I had an x minus 2 there already, times the 2. So this will cancel, and it's just 1 over 2 that's left, and the limit of a constant is the constant. So our slope on the piecewise, when we're coming from the left, is 1/2. Aiden. You factored it out. That's fine. Same deal. That's good. F prime of 2 coming from the right. So the slope of the piecewise function at 2 coming from the right really just wants us to evaluate what the slope is of this function at 2. So limit as x approaches 2 of f of x, which is root 2x in this case, minus f of 2, which is 2, over x minus 2 again. Direct evaluation, 0 over 0. Manipulation, multiply by a conjugate, root 2x plus 2 and root 2x plus 2. I'm not going to multiply out the denominator. I am obviously the numerator. So root 2x times root 2x is 2x. Outer and inner cancel, minus 4. Just some formalities with all that other stuff. Now your numerator is pretty clearly factorable. So if you pull a 2 out and you're left with x minus 2, you lose the x minus 2, which was the 0 over 0 culprit. And now we have 2 over the square root of 2 times 2 is the square root of 4, which is 2. 2 plus 2 is 4. 2/4 is 1/2. So our slope from the left is 1/2. Our slope from the right is 1/2. Our slope is the same on either side. Voila, it's differentiable at 2. Okay? It is tough to write those so that they work out. Thank God I let the software do it and I just take their questions. Because I've tried to write them and it's really hard to make them continuous but also make it such that the slope is the same. It's a tough thing. But anyway, your homework for tonight is kind of picking up where we left off last night. 79 to 84 all. You might find that a couple of those evens we already did. And then 88 to 90 all.